Good afternoon. I'm Michael Thompson from Procter & Gamble. And today I'll talk about one of the new features that Lionel mentioned yesterday. My talk's Understanding Your Customer Using the Most Relevant Explanations, or the MRE feature in BayesiaLab. And this is one of those features where I wish we could say we influenced Lionel to add, but it's one where on two independent threads, he was looking at adding this to BayesiaLab, these types of capabilities, and I was doing some research. And as I fired off the email to him and asked, can you add this to BayesiaLab? He responded, oh, I'm looking at this for BayesiaLab, and now it's there. And so we're really happy to have something this powerful. It's something that I'd been working on, mainly using tools like R and the packages there. So my talk just has these four pieces: why and what are some of the applications, what is MRE, what is the most relevant explanation, how to use it in BayesiaLab, and then an example, understanding the customers. So the motivation is, with much of our work, and there are many ways of doing this in BayesiaLab, is we need actionable insights, and we'd like to know where to intervene. We want to achieve something, so what can we actually move to achieve what we need? The next, we need to understand how our machine learning systems are behaving. We don't want a black box that we can't understand. One of the best things about a Bayesian network is it's so transparent. But when you have many nodes, it gets very complex, and it's this huge combinatoric explosion of different possible state combinations. And this tool is great for exploring that. We need to distinguish classes or groups by their most discriminating traits, or the things that are most representative of, say, a specific consumer segment or a cluster that you form. And this technology, or at least the major metric that I'll go over, or Lionel introduced it yesterday, is great for that. And finally, we need to discover interesting cases in our big data. So one of the ways you can use this technology is when you have a large database, you can find those cases that meet criteria that are really representative, the perfect exemplars, if you will, of a given consumer segment or a given scenario that you're trying to identify. So in each of these, so in the explainable AIs, for example, if you have a recommender application recommending products to a consumer, you can instantiate as evidence, assert as evidence, a profile for that person, what type of person, their demographics, their interests. And then the hypothesis is, what option to offer them. In this case, if it's a product recommender, what sorts of products would be most representative of that consumer? And you can rank order them and give back a list. So you can identify what's best to provide that customer. Similarly, with classifiers, you might want to know, why did our deep learning neural network classify a person is high risk? In that scenario, you have the person's profile again and this class designator, high risk. So what is it, how strongly is that related? And how strongly can you score high risk for that consumer versus, or that person versus any of the other classes they might have been assigned to? Another is, again, looking for specific exemplars in a database. Given specific traits, you can then score every single case in your database and rank order them as which are most representative, which are the best exemplars of those traits. And it's more complicated, or you get a richer insight than merely just a SQL filter, a database filter on specific criteria. And then finally, on causal inference for intervention for fault diagnosis, medical diagnosis, if you have a causal Bayesian network, you'd like to know exactly what are the most likely diseases, what are the most likely faults that explain the symptoms that you observe. And so I'll try and use that convention of green for the evidence being asserted and yellow for the hypotheses that represent the explanation of that evidence. And so as Lionel had mentioned, this work, the paradigm we're using comes from Yuan and et al. Their paper, Most Relevant Explanations in Bayesian Networks. And it goes through a nice derivation of starting with a so-called generalized Bayes factor and identifying criteria to efficiently search this huge space of possibilities. The generalized Bayes factor has its origins all the way back to Alan Turing and I.J. Good, as they were, doing cryptography and code breaking back in World War II to, I guess, to understand or decrypt the Enigma machine. But one of the key distinctions I wanted to make here is it's not the same as the Bayes factor that you'll often see listed for model selection. And one of the big distinctions, and there's, I've talked with some statisticians and they come up with all sorts of reasons why Bayes factors might not be optimal for model selection. There you may have an open universe. There are more models than what you're considering. And there's a question of what would the real prior be or a best prior be on the models. That's not relevant in our scenarios here where we have this closed universe really of all the space that the Bayesian network is describing. That's your closed space, that's your variables, the states that they can be asserted, that defines the universe. In that space, the most relevant explanation, you can, in theory, you could exhaustively just enumerate every single case, give it a GBF score, rank order them. Of course, the combinatorics are so large, you need very smart ways of doing that search. And BayesiaLab has one of the smartest because they have one of the smartest developers, and they use a genetic algorithm that goes through and identifies these cases by looking through. And usually you cap it like, I want the K top hypotheses to explain these examples in this evidence. In that by Yuan and all, they call that the KRE, the K most relevant explanations. I just put links in the PowerPoint. In the PowerPoint, it's fine to make it available to everyone. It captures some of the, again, going back to Good, a nice review, the weight of evidence, which is just the logarithm of the GBF value, and some of the background research that helps you understand why it works the way it is, why it's impactful. So for example, Tenenbaum and Griffith, they look at the rational basis of representativeness, and you might think of the R as another way of saying most representative explanation, which hypotheses are most well represented by those the evidence that's asserted. And then there's the philosopher Fiddleston, who cast it into the context of the philosophy of science and how people reason under uncertainty. So while Tenenbaum and Griffith explore it as how do humans learn and how does the brain develop, and you begin to recognize things as representative, Fiddleston looks at it in the larger sense of how humans reason under uncertainty and come to conclusions in a general way. Oops, I think I pressed the wrong button. Okay. So again, the foundations are there in the generalized Bayes factor. So mathematically, what is it? And it's usually written in two primary ways. One is sort of you can think of it as a generalized likelihood ratio, and that's the probability of the evidence given the hypothesis divided by the probability of the evidence given not the hypothesis. And this is really quite rich, since either the E or the H can be any combination of variables and any combinations of states. So you can have a very involved and complex evidentiary profile describing a person that you're asserting, and you can look through this space and find any number of variables that would be a very good explanation for that that evidence or that profile. The other way of writing it, and it's perfectly equivalent, just apply Bayes' rule and work through the algebra, is as the odds of the hypothesis given the evidence divided by the odds of the hypothesis. In your classic E being the asserted data and H your hypothesis updated from your prior, that's just the posterior odds divided by the prior odds. And so you're really just seeing how much did the evidence move you to even being more strongly in favor, the odds in favor of the hypothesis you're looking for. So you can imagine with a large Bayesian network with many nodes and many states, there are many possible potential hypotheses that could be found. And so BayesiaLab efficiently searches through and finds them. So I've given two examples here, one written in the odds ratio format and the other written in the generalized likelihood ratio format. There's nothing, there's no primacy here or definitive way. It could have been written either way, but I find it more naturally to write it, and my next slide actually speaks about this, where the clause, if you think of it more in a causal way, like a shopper buys these products, or a disease or a condition causes these symptoms, you would choose the way that's conditioned on the cause and go more towards the effect. That's a sort of general rule of thumb, but it doesn't necessarily have to have a causal implication. These are, you can choose whichever you want on the E and the H. But so for example, in the product recommender, you might have as evidence that you have a high income shopper. And then you might want to search over all possible products in your catalog or in your supermarket to find which are those that are much more representative of folks like that, or more relevant to a consumer like that. Now it's a bigger issue than just finding the posterior probability. So, you know, what's the probability of H1, which is bread, given the high-income consumer? Because pretty much everybody buys bread in general, or a lot of people buy bread. So probability bread given almost any evidence is going to be relatively high. And so you don't just want to go to those conditions that are most probable. For this scenario, there are many scenarios where, yeah, that's exactly what you're looking for, the most probable state. But here we're not looking for the most probable. We're looking for the one that's most distinctively representative of the evidence, the high income consumer. And here I've just chosen as a product artisan cheeses, for example. And if you put it in the posterior odds over prior odds format, it's reasonable to expect that the odds of having artisanal cheeses amongst higher income consumers would be greater than that of the odds of just finding it across all consumers in general. And so that would score a higher GBF for artisanal cheeses than it would for bread, and rank the cheeses higher. Similarly, for the medical diagnoses, you may have multiple types of potential evidence that could be asserted as symptoms, and you can have multiple conditions. So you could look at it either one way, like for example, saying that given a patient has a runny nose, what's the probability of that symptom given either one of the conditions, divided by what's the probability of that symptom divided by not having that condition. And that would rank order those two conditions with respect to that piece of evidence. When you find that with runny nose, there may not be that big of a distinction between folks who have pneumonia and a cold, because runny noses are pretty common, and it's also not that surprising that someone with pneumonia might also be susceptible and have a runny nose. but as a piece of evidence, having a positive X-ray is much more indicative of someone with pneumonia than it is of someone with a common cold. And so as far as evidence that discriminates strongly between them, you would want to, look for, give the patient an X-ray to distinguish whether it's just a simple cold or whether they have pneumonia, or you might, or given a positive X-ray, you would be much more certain that they were suffering from pneumonia than if they were suffering from a common cold. So again, which way you write it, just mathematically, it's equivalent. It really comes down to the interpretation and how you want to explain the findings that come out. So within BayesiaLab, I'll show an example here where we have a car dealer, and then this is one where I chose the example and found the stock photo from Microsoft in PowerPoint and just put it up. Then I realized it's actually Mercedes, not talking cars. So Stefan, you have to kind of close your ears over this example because you know the real of this. But this is a hypothetical case where we're using hypothetical data, but a consumer really is just trying to identify what's the issues with their profitability as they change. There are any number of potential questions they could ask, but one might be just trying to distinguish what sorts of behaviors and what sorts of attitudes they've observed among their highest profitability customers as compared to their lowest profitability customers. So you can imagine they can, have customer satisfaction surveys that they have issued to all of their both service customers and vehicle customers, and they've got the customer relationship information, all the services used, which vehicles purchased, how recent has the relationship been involved, and how frequency, and even how exclusive that relationship is between that consumer and that dealer. Are they the only dealer they go to, or do they have multiple dealers? The models, in all of our analysis, this is very similar to what we would do with certain surveys. But in all of our analyses, we do multiple models. One of the easiest and most basic are just building association networks and doing exploration, just trying to understand what you have in that data set. And I'll look at that as the associative BVN. But you can also, as Lionel suggested in the last talk, you could do variable clustering, forms, pseudo factors or latent variables, and then build a more structurally causal explanatory model amongst those factors and get greater insights that way. What I'll show here again will be just with the associative network. So this is the network in this case is built off of the variables. The color coding corresponds to this legend here. So we've got a assortment of things like which locale are they from, their age, income, household size, et cetera, for the demographics, different attitudes about the automobile in their life. For example, an image, this one here, my image is tied up in the car. There's others such as a car is just a matter of wheels. I don't care. It's just transportation, et cetera. The departments, whether it's service or sales that they've used, which types of vehicles, luxury vehicles, basic vehicles, et cetera. The relationships, recency, and how satisfied were they with things like the quality, the convenience, the cost, the value proposition of the relationship. And then we know how much that customer has spent on all of the services and all the vehicles. And you can imagine doing some analyses where you have some good metrics then on the profitability. The overall profitability score is in the center, and there are others around different aspects of the profitability for that consumer. or that customer of the dealership. And so we can build such a network and then ask questions such as around profitability by trying to identify what distinguishes the dealers most profitable versus the customers who are least profitable for the consumer. So I'll just quickly go through the steps of how this is done in BayesiaLab. The feature itself, at least in version 8.1.3, appears under Visual Report Evidence, Most Relevant Explanation. And so when you get into BayesiaLab in validation mode, the first thing you need to do is actually assert the evidence that you're performing the analysis with. In that analysis, that evidence analysis, there are other features within BayesiaLab to do to understand the evidence. But in this one, similarly, here we'll select the overall profitability score. It's a 5-level metric. And we'll just define high profitability as top 2 box on profitability. Use soft evidence and assert it. In general, we could have used any number of nodes that define the case we're interested in. And we can assert hard evidence or soft evidence or any numeric evidence we choose to. So after you've asserted that in the graph pane, the type of analysis we're doing, we want to focus on specific types of variables as potential explanatory hypotheses. So you go into the graph pane and simply select those. In this case, we want to give every variable except the other profit metrics a chance to be part of the explanation or part of the hypotheses providing an explanation. So all the nodes are selected except the dark green ones, which are other profitability nodes. And so those are the selected nodes. Then, as I showed on the previous slide, you go to the analysis, report, evidence, and most relevant explanations, and the dialog box pops up. You leave the selecting nodes as the option for the candidate set of hypotheses that BayesiaLab will search for. As Lionel explained the filtering power, that comes down to which explanations dominate others. The strongest filtering, you'd have both weakly and strongly dominated. That would be setting 2. At setting 1, you only have strongly dominated, meaning if you have a simpler explanation, it requires just 2 variables to explain the evidence, and it has a higher GBF. It's both simpler and it's more powerful, or it has a higher score. It's going to dominate any other hypothesis that contains those 2 variables set at those 2 states. So anything more complex is just, it'll just hide that. At 0, it just shows everything. It just rank orders all the combos it finds. So you click selected nodes, filtering power of 1, and click OK, and it performs the search. The other pieces are all around the genetic algorithm and tweaking that. So what results is a report that's very similar to many of the other analyses reports in BayesiaLab. Here, I've modified it a bit by just copying it out of the report window, putting it into Excel, and adding more text just so it's easier to see. Usually these are the comments for the nodes, so those would be little hyperlinks that can pop up in the report when you're interactively working with this. I've just put them outside of the hyperlink. I also added a column. This column doesn't naturally appear, but it's derived directly from the posterior odds. The posterior probability is just the odds in favor divided by the odds in favor plus 1, and that's what this column represents. And as you can see, these were the candidate variables that were selected for the hypotheses, and these are the states that they were asserted to. The MRE size, well, this just involved 1 variable, so it's 1, 1, etc. The weight of evidence is the log of the generalized Bayes factor, which is reported here. And since the generalized Bayes factor is made up of a likelihood and the posterior odds, BayesiaLab also reports that information just so you can see. So for example, there's some scenarios where you can have a very large GBF, but it's only because the probability of, say, the probability of E given not H is so infinitesimally small that it's almost zero, or literally can go to zero. And PE given H could be almost just as small, but maybe 100 times bigger. So you'd get 100 for your Bayes factor and think that's large, but it's almost an impossible case. So you would like to also, you always want to check to see how reasonable these values are, like are the cases reasonable? And as you can see, they are. In fact, they're very substantial here. So a lot of the Bayes factor being so large is driven by the fact that the likelihood or the posterior odds themselves are reasonably sized. So as far as interpretation for this specific example for the first hypothesis, you can read it off as the probability of finding a high profit or high profitably consumer or customer amongst well, who did not buy a basic SUV. That's what this this variable represents. The vehicle purchase was basic, and it says no. So they did not buy a basic SUV. It's 5.8. It's about 6 times higher than it is amongst all the customers who did buy a basic SUV. So that's the likelihood version of it. Probability of our evidence, the high profit given not buying, divided by the probability of high profit given that you did buy the product. So similarly, you could go through and read off the interpretation for each of these and identify which of the consumers, which are the most likely to have been high profitable customers. Now, what actions you might take then, that gets into policy and other aspects and opportunity that you might have. One thing that should be noted is you can interpret the generalized Bayes factor as the Bayes factor is interpreted in general. Just from Wikipedia, you can look through and see that, for example, there's a build on this, Stefan. If you, oh, actually, I'm sorry, I forgot I was controlling the little blips myself here. But as the table shows with bits and the K, this is the Bayes factor level. Bits is the weight of information, weight of evidence in a log base 2. And weight of evidence here is reported in log base 2. And the Bayes factor here. So you can think of this as a way of interpreting the strength or whether it's reasonable. And really there's about a cutoff, like the first 3, potentially the 4th. I.J. Good claims that people really can't discern anything greater than like anything less than about a 0.3 difference on the weight of evidence. So something 0.3 or greater really separates them as something that where you would notice the difference in proportions. But so this gives you a clear idea of those things that are most strongly associated with the higher profitability customers than not. And then similarly, I just asserted the evidence. Now, as you can see, the evidence has been asserted as soft evidence on the bottom 2 states and run. And we find out that the people who strongly agree that, you know, a car is just a pair of wheels, it's just transportation, those are those amongst the lowest profitability customers. Also, those whose relationship, the exclusivity is very low. Like they see many other, or go other places for service and vehicles. They've bought their vehicles at a number of dealers and they service their car other places. Those are also considered the lower profitability. So those are, this is just an example of the sort of output that you get and how it lends itself to a relatively intuitive interpretation of, you know, what's the most strongest thing that these people have in common or these cases have in common. And having this information too, one thing I didn't note in that dialog box is there's a section for defining, for specifying whether you want to augment your evidence scenarios with the information or not. And that's very helpful because now that you've got your evidence scenarios in the monitors, you can run through each of those individually, asserting the evidence and looking at them. And you can also use those as filters for selecting out cases within your database. So for example, one, just in checking all the correctness of Lionel's calculations, I would save these things to the evidence scenarios and then do batch joint probability inference running and things like that. And you can score all your cases in that scenario and check those. Or you could score a whole database and see just how reasonable the cases are. And so in conclusion, basically MRE is a useful way to get at some of the why, like you're getting a high probability when this evidence is asserted. What are all the other possible states of variables in that space defined by your Bayesian belief network that are very consistent with that, are most representative or most relevant to having that information. So it's a very powerful way of querying that whole universe. It's also a way of finding out, you know, what's atypical or anomalous. If you just look at the math, if you say if you have a hypothesis that gives a high GBF, doing not GBF is just the reciprocal. That's just the math. But not on these hypotheses, that's a full negation of all conditions. You might want to also, element by element, variable by variable, and state by state, want to see which of the cases literally give the most negative GBF, and those would be the least representative. And I don't know what proportion of our folks were here from last year, but I presented a college exploration tool. And one of the features of that, for each college, it would generate a most representative profile of students, what majors, what how their performance on SAT, et cetera. But it also would go through and identify what were the least representative students on that campus. And you could use the same strategy, but just reverse the ordering for that. MRE is based upon the generalized Bayes factor, and it really has some sound theory and underpinnings in a lot of dimensions that make it quite a good metric for these. And I've used the generalized Bayes factor. In that tool, I take the log of it and use the weight of evidence actually as the predictors for any proportional quantity. So for example, I have a college, I have percent African American, percent white, percent Hispanic. I turn those actually into generalized Bayes factors and actually the weight of evidence for each of those ethnic groups. So you take the proportions, turn them to odds, take the odds ratio relative to the general population, and then you take the log of that. And actually those as factors, because most of the selections have very much in common with like doing a logistic regression. So this ends up being another log of an odds ratio term in a logit regression. So it has very clear interpretation and very nice one-to-one relationship with the latent logit variable you get out and the resultant probabilities for logistic regression. And I've actually found to get stronger identification of certain variables in building models that way in a number of different contexts. And finally, the actual model you use for the BBN, it's very important. And it dictates the limits of how useful the information is, what purpose you can apply it to, but also, especially if you're doing causal inference, you need a strong causal model so that those diagnoses make sense. I have applied this to, for example, the famous alarm network about cardiology or cardiac patients, basically, and the conditions that can come up. And it's really quite telling. It identifies under different symptom scenarios what are the most likely conditions that would cause it. And then finally, the biggest conclusion is that BayesiaLab once again strengthens its position as really the leading state-of-the-art tool for Bayesian machine learning. There's no substitute in my book and in the work we do. So that's all I have. So thank you.